In this session, we're going to see an introduction to functions and function notation. And we start out with a definition. A function is a mapping between sets in which each input corresponds to only one output. The set of inputs is the domain and the set of outputs is the range. In terms of ordered pairs, a function is a set of ordered pairs in which the first coordinate is not repeated. That is to say, domain elements are not repeated. And since the first coordinate or domain elements are not repeated, this can be looked at graphically. And what we're going to consider now is the vertical line test. And probably the easiest way to express the vertical line test is that any vertical line touches a function in at most one place. So let's look at a couple of graphs. And here we have on the left a graph that has the property that a vertical line will touch it in more than one place. And so if we kind of just look at some possible values here, let's say that at the top where the vertical line touches we have a y-coordinate of A, and at the bottom we have a y-coordinate of B. And each of those, say, has an x-coordinate of simply x. Then the point at the top has coordinates x comma A. The point that's at the bottom has coordinates x comma B, and now we see that a domain element is repeated if we were to list this as ordered pairs, and that violates what we call the vertical line test. And so this is not a function. It's a relation, but it's not a function. In the one on the right, any vertical line that I try to pass through this graph touches at most in only one spot. And so this is the graph of a function. This is what it looks like to pass the vertical line test. Finally, we're going to look at this from the perspective of a diagram. And if I have a set that maps, let's say A and B to values 1, 2, and 3. Let's let A go to 1 and A go to 3 and then B go to 2. If I express this diagram as a set of ordered pairs, then I have A1, A3, and B2. What we see is, again, a repeated domain element. A shows up twice. That's not allowed to happen in the case of a function, so this is again not a function. Conversely, if we have a set, say A, B, and C, that maps to, let's say 1 and 2, in such a way that, say, A goes to 2, B goes to 1, and C goes to 2, then when we list this as a set of ordered pairs, we have A2, B1, and C2. And we can see that the 2 is repeated, but the 2 is not part of the domain. It's part of the range. And so all of our domain elements are, they appear only once. And so here we have a function. And now we can write down, say, the domain of this function, which is the set that contains A, B, and C, all the first coordinates, and the range, which contains 1 and 2. Those are all the second coordinates. Well, for much of our work, we're going to be dealing with equations. And so let's look at this description. An equation defines y as a function of x if we can solve for y by adding, subtracting, multiplying, dividing, or taking odd roots. Now let me be the first to tell you that this is not the whole story, but it's going to work for now. And this description here, when we say by adding, subtracting, multiplying, dividing, or taking odd roots, I'm going to say that's what we're going to refer to as easily. If we can easily solve for y, then we're going to see this is a function. Again, the fuller story comes down the road. So let's look at our first example here. Determine if the equation defines y as a function of x. Well, notice that we set up here that we're concerned with if we can solve for y. And in this first equation here, we've got y equals 2x plus 3. It's solved for y. That being the case, we're going to say yes, this is a function. For the second equation, we have x squared minus y equals 4. And again, the name of the game here is, can I solve for y easily? Well, if I subtract x squared from both sides, I have negative y equals negative x squared plus 4. And then say multiply by a negative 1 on both sides, I have y equals x squared minus 4. And now I'm able to isolate y, and we did it easily. So the answer here is yes, we have a function. Next we see y squared minus x equals 4. Now at first it looks like we can easily solve for y. We have y squared is equal to x plus 4. But at this point I'd have to take a square root. Now that's an even root. And so let me note that this is an even root. And the reason that this is going to cause us some problems is, remember, whenever we square root both sides of an equation, we have to remember to throw in a plus or minus. So I end up with y equals the square root of x plus 4. And now all of a sudden, if we consider, say, an xy table, and I put 0 in place of x, the answer is the square root of 4, 2, or negative 2. This would actually lead us to ordered pairs 0, 2, or 0, negative 2. And now we see we have a domain element that's repeated. So the answer here is going to be no. This is not a function. And what we saw is that this time we had to take a square root, which was an even root. Next we have xy equals 3. And we can solve for y by dividing both sides by x and get y equals 3 over x. May not like how it looks, but we were able to do it easily according to the description I gave earlier. And so we're going to say this is a function. If the question is it a function, we would say yes. Describe whether or not it's a function, we can say yes, it's a function. However you want to express that. For the next equation, we've got absolute value of y equals x. There's not an easy way for me to get to get y by itself. And as a matter of fact, if we consider an xy table, whether we let y equal negative 3 or positive 3, the x value associated would be 3. We have a situation that's similar to what we had above with repeated domain elements. And so the answer here is going to be not a function. In the next example, we've got 2x plus y cubed equals 7. So let's see if we can solve for y. We've got y cubed is equal to negative 2x plus 7. And now what I want to do is take cube roots of both sides. Well, the first thing I notice is that a cube root is not an even root. It's an odd root. Odd roots fall in the description of easily solving for y. So this actually turns out to be a function. Notice when you take an odd root, as in this case, we don't need that plus or minus, which got us in trouble before. Okay, we're going to shift gears a little bit and see what function notation is about. And then we're going to see how to find function values. First, the notation. Just some vocabulary here. We've got f of x equals 2x plus 3. And as far as the anatomy of this thing here, the f is the function name. The 2x plus 3 is the function definition, or could be considered the rule for generating outputs. The x, where we have f of x, this is called the argument. And I want to make a note here. This is not multiplication. It is read f of x and is just function notation. This f of x business is really another way to write y. In other words, f of x is equal to y. Now we're going to find function values, and for better or worse, this is something you've already done. This is not going to be new. Instead of an xy table, I'm going to use an f of x table to show you just how this notation is not a new concept. It's just really a different way to look at something you've already known. I'm going to pick values of 2, -4, and 0 for x and put them into the function, which, as we recall, is f of x equals 2x plus 3. If we want to evaluate f of 2, what that means is we're going to put a 2 in the function rule where we saw an x. So in this case, we just have 2 times 2 plus 3. This is just like cranking out points when you were plotting lines. Plotting points to graph lines, that is. So 2 times 2 is 4 plus 3 is 7. And so here we have that f of 2 is equal to 7. To find f of -4, we're simply going to put -4 in place of x wherever we see it in the rule or the function definition. And so f of -4 is 2 times -4 plus 3, and if I can do my math right, that's -5. And so what that indicates to us is that f of -4 is equal to -5. Again, it's just like doing an xy table, except now when we write down, say, f of 2 is equal to 7 or f of -4 is equal to -5, it gives us a little bit more information. It tells us what y is for a particular x. Finally, we're going to look at f of 0, and that's going to be 2 times 0 plus 3, again putting 0 in place of the argument, and the answer there is of course going to be 3, and so we can say that f of 0 is equal to 3. Now, just to wrap this up into a context with which you're familiar, we can say hence 2, 7, -4, -5, and 0, 3 are on the graph of f. In other words, we can wrap this up into ordered pairs of the type that you're familiar with. Okay, on to our next example. Here we have a function f of x equals x squared plus 7. We're asked to evaluate it for particular x values, the first being 3. So we're supposed to find f of 3. As you recall, that means that I'm going to be putting a 3 in place of the x, in place of the argument. And so I have 3 squared plus 7, which is 9 plus 7. And last I checked, that value is 16. Oops. And last I checked, that value is 16. And so we would say f of 3 is equal to 16. Next, we're asked to evaluate f of -4. It's the same rule. So -4 squared plus 7. And notice I put the -4 in parentheses. That's because whatever is inside the argument, in this case -4, is to be squared. And as I'm sure you recall, when you square -4, you get a positive 16. Adding 7 to that gives me 23. And so I can say that f of -4 is equal to 23. Next we have something that looks a little weird, f of 2a. Now let's kind of scroll up and see what we've just done. Originally we had f of x equals x squared plus 7. And what that indicated to us was that, for instance, when x was 3, we would put 3 in place of x, 3 squared plus 7. When the argument was -4, we squared -4 and added 7. Now what we're going to do is we're going to take that 2a and put it in place of the argument as we've been doing. And so those parentheses indicate what it is that you're doctoring, if for lack of a better word. And so here I have 2a, the quantity squared, plus 7, which squares to become 4a squared plus 7. And there's not any other way that I can clean that up. I don't have like terms to collect or anything. And so f of 2a is simply 4a squared plus 7. Again, this is just exploring function notation, which we'll do with the last example here, the last example of this type, f of x plus h. And what this means to us is we're going to put x plus h in place of x in the original expression. And so what that means is I'm going to square the x plus h. And so I'm again going to use parentheses to indicate that I'm squaring that whole quantity. And when I do, remember we're squaring a binomial. There's a pattern for that. We get x squared plus 2xh plus h squared plus 7, because that 7 was along for the ride. And that's what we're going to say that f of x plus h is. At this point you may be wondering, like, why would you possibly need to know that? Just building up stuff for down the road, and it's getting to know function notation. Now, having explored function notation, we're going to turn our attention to one of the ways that we're going to use to analyze functions. We're going to do a lot with functions, and part of that analysis is figuring out allowable inputs and outputs. Let's recall that the domain of a function is the set of allowable input values, and the range is the set of output values. And what we want to know is, what are we allowed to put into the function? What kinds of values are we going to get out of the thing? In a lot of cases, finding the domain is a lot easier than finding the range. What I need to ask myself is there anything that I'm not allowed to do with a particular expression? So in the first case here, find the domain of f of x equals 2x plus 3. I want to focus on the variable 2x plus 3, the x right there. Is there any number that I'm not allowed to multiply by 2 or to add 3 to? The answer is no, and so the domain here is all real numbers. Now, it doesn't really make a lot of sense right now, but it will make a little bit more sense in the next example. Next, we have g of x is equal to the square root of x minus 1. And we want to keep it real, so we want values such that x minus 1 is at least 0, greater than or equal to 0. Solving this inequality gives us that x is greater than or equal to 1, and we can just wrap set notation around that and say it's the set of x such that x is greater than or equal to 1. That's what we can identify as the domain. And if we wanted to, we could express this as an interval 1 to infinity, and that's a square bracket with 1. Finally, we have h of x is equal to 2x plus 1 over x squared minus x minus 6. First thing I want to do is consider what happens with a fraction. We can't have the denominator equaling 0. So let me find out where the denominator actually does equal 0 so I know what values to exclude. So I'm setting the denominator x squared minus x minus 6 equal to 0 to find those problems. Solving this requires factoring, so I have x minus 3 times x plus 2 is equal to 0, and that equation is true if x is equal to 3 or negative 2. So what we're going to do is we're going to exclude those values, turn it into x is not equal to 3 or negative 2, wrap set notation around that. And so we have the domain is the set of x such that x is not 3 or negative 2. Those are the two values which, when put in the x's in the denominator, would make it equal 0. We could give this an interval notation, but it's much easier in set notation. Oh, you want to? Fine. Okay. The set from negative infinity to negative 2 parenthesis at -2 because we can't include it, -2 to 3, and then again union with 3 to infinity with parentheses all around. It's a double punctured number line if you really like. I think it's just easier with set notation. So for right now, our considerations for domains are going to be, we want no negatives inside a radical with an even index. We also want no instances where the denominator of a fraction is equal to 0. As long as we can exclude or avoid those two situations, then we're going to be okay for now. That picture will get more interesting down the road, but that's all we need to worry about for now. Finally, we have directions here to find the range of f and g above. And what I skipped right past is, you notice the first function we called it f, the second function we called g, the third function we called h, and it's like children, you name them different names so you can tell them apart. The range of f of x equals 2x plus 3. Let me rewrite that down here. In fact, let me rewrite both of them. Well, if x goes infinitely small or infinitely large for f of x equals 2x plus 3, then we're going to have values that are also from negative infinity to positive infinity. In other words, the range of f is all real numbers. As far as g of x is concerned, remember g of x was equal to the square root of x minus 1. This is going to always be at least 0, right? Greater than or equal to 0. And so the range for g of x is going to be the set of y such that y is greater than or equal to 0. And that's simply because square root won't ever be negative.